All right, so quick review of the new concepts from yesterday. So Descartes' rule of signs. Descartes' rule of signs just says that if we look at a polynomial, f of x, we just call it f of x, right? We're trying to find the number of possible real positive zeros and negative zeros of that function. You just look at the sign changes of f of x to find the possible number of positive real zeros that you have, right? So in this case, we had 1, 2 sign changes. So we could either have 2, or then we move down in increments of 2. So either 2 or 0 positive real zeros. One of those two has to be the case. We take the function and we evaluate it at negative x. And all that really does is it's going to leave the even powers of x. Those terms don't change. They stay the same. The odd powers of x, the signs of their coefficients will flip, right? They'll change signs. So in this case, the x to the fourth term would stay the same. The x cubed term would change from negative to positive. 6x squared stays the same. The 4x term changes from negative to positive, and the constant stays the same. So again, we just ended up with 1, 2 sign changes in f of negative x. So that tells us we're either going to have 2 or 0 negative real zeros. Okay, that's all that tells us. It just gives us some possible different outcomes for the number of zeros we have. You'll see today when we start looking at doing some some bigger problems together, you'll see why that's useful. Okay. Then we were talking about kind of reviewing a problem that we had done earlier, right? We said that if we're told that we want to build the simplest polynomial with integer coefficients and these 3 zeros, all we have to do is convert those zeros into factors and then multiply the factors together to get the polynomial, right? So x equals 5 halves, that converts to the factor x minus 5 halves. But if we don't want any fractions, we could just take this and multiply through by 2. And that's okay to do, because think about the context in which we're doing this, right? Normally, we would start with x minus 5 halves is one of our factors, right? That's set equal to 0. I guess I don't even need the parentheses there, do I? I have the factor x minus 5 halves that I set equal to 0 and solve to get the 0, right? Well, that would give me the 0, x equals 5 halves. But I could just as easily, if I wanted to, I could multiply 2 through the entire equation, right? I could distribute a 2 through there, and what's that going to give me? Then I would get 2x minus 5 equals 0. Okay, so then the 0 of that factor would also be 5 halves, right? So point is, we're not going to use this factor because we want integer coefficients. So we're going to use this one instead, right? But you see what I'm saying? Give me 1 to 5 on that. Does that make sense? So these zeros ultimately led us down to these, and that should have been a plus, right? Led us down to these factors. And then we just multiplied all those together to get that polynomial. So there it is. There's the simplest polynomial with integer coefficients that started with those 3 zeros that I gave you, right? Okay, so now, new problem. Okay, we're going to start where we left off with that polynomial that we just built from those factors. And I want you to solve a different problem. I want you to make a list of all possible rational zeros. Okay? Now, what we need to know here is that we want to try to trace the evolution of the leading coefficient and the constant, right? How did we get that 90 as our leading coefficient in our polynomial that we built? Well, it came from the product of each of the leading coefficients, didn't it? When we distributed, right? 2 times 5 times 9 gave us 90. How did we get the 300? Well, that came from when we distributed and multiplied through each of the three constants, right? -5 times -6 is 30 times -10. Oh, that's supposed to be a plus, though. Remember, that was supposed to be a plus. That was a plus. So we got 30 times 10 is 300, right? Okay, and let's think now, if we're trying to figure out what were the possible rational zeros, well, okay, where did ultimately the 2 and the 5 and the 9 come from? Think back what we just did yesterday. Where those actually came from was our original zeros. Okay, so the 2 and the 5 and the 9 that multiplied to 90 started off where in our zeros? In where? The 2 and the 5 and the 9 were the denominators of each of the zeros, right? See what I'm saying? Right? So it was the product of the denominators that gave us the leading coefficient, right? Where did the 300 come from? Well, that was the product of each of the numerators, right? Everybody see that? So then this ought to work in general. Like if I didn't know where those came from and I wanted to make a possible list of all rational zeros, well, then the denominators would have to consist of all the possible factors of 90, wouldn't they? See what I'm saying? Right? Because I know that the denominators multiplied to 90. I don't know which specific denominators they were, though, if I don't know where these came from, right? If I didn't know what these factors were, if I just started with the polynomial, I would have no idea what the original denominators were. All I know is that they multiplied to 90, okay? So then I would make a list of both the positive and negative, all the positive and negative factors of 90. Well, that would be 1 goes into 90, 2, 3, 5, 6, 9, 10, 15, 30, 45, 90. That's a lot of them, right? That's a lot of possible denominators. What about the possible numerators? Well, those came from the constants which multiplied to the constant of our polynomial, right? So the numerators would come from the list of all possible factors of the constant. That's all the possible factors of 300. Yikes, that's a lot, right? What are the factors of 300? All of those numbers are, okay? So then the possible rational zeros would be every fraction I could make out of the green numbers divided by the yellow numbers. That's a total of 330 possible zeros, okay? That's a lot, right? That's a little bit daunting. I mean, to think you'd have to try potentially 330. And how did I get 330? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different denominators, right? Times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different numerators. So that gives us 15 times 11 is 165, but they could be positive and negative also, right? So I got to multiply that by 2. Yes. Oh, I'm missing 18? Ah, okay. Okay. Does 18 go? Yeah, 18 goes in there, doesn't it? Right. So there could have even, okay, so there were even more. So it would have even been 18. That's going to give me another, so man, that's going to give us 12 times, you're saying it should be 12 times 16 times 2. So it's even bigger, right? Okay, so then we've got all these different fractions we could make. Yikes. That's a big number of them, but it's smaller than infinity. So it does help us a little bit. Now, if we use Descartes' rule of signs, we could even whittle that down more potentially, right? Because we'd know, as I start to find these zeros, I might be able to cross off a bunch of them based on what I know Descartes' rule of signs tells me, okay? Okay, so then in general, this is what we call the rational root theorem. All rational zeros, zeros that can be written as fractions, must be included in the list of fractions we can build by dividing factors of the constant by factors of the leading coefficient. Okay. So how would we use the rational root theorem to find rational zeros? Well, we would determine what all the factors of the constant and the factors of the leading coefficient are. We'd write all the possible fractions we could build from those. And notice that some of these fractions, by the way, it would be a little bit less than we said, because some of these fractions are going to simplify to the same thing. As an example, like these are the numerators. So what if I did 5, like 5 over 10 would be the same as 10 over, let's see, or like, how about this? 1 over 2 would be the same as 5 over 10, right? So a lot of these are going to end up being the same thing and they'll go away. Okay, and that happens quite a bit. But so the list would be a little bit shorter, still pretty long. We're going to make all those possible fractions, and then we would determine which ones work by evaluating the polynomial to see where we get no remainder, using synthetic division, of course, right? Because that's easy to do. And I'll show you a real convenient way to do tabular synthetic division, where you can just try a number. You don't have to make the bracket each time. You just do it with a single row. You'll see what I mean. It makes it way, way, way easier. Okay. So let's try some problems. One like this. Okay. Without using a calculator, find all the roots of the equation below. Okay, it's a 4th degree polynomial. We don't know how, there is no factoring pattern for a 5-term polynomial that we know. So we have no option here but to try to find 1 0 at least to get the ball rolling, right? To make this thing smaller by using the rational root theorem. But the rational root theorem here is going to be easy, isn't it? Easy, easy. Think about the different fractions we could build. We're doing the numerators are factors of the constant. The denominators are factors of the leading coefficient. Well, what's the leading coefficient? 1. That's great. That means the denominators are going to be 1 no matter what. And my fractions are all going to be integers. Give me 1 to 5 on that. Does that make sense? Okay. So then I've just got factors of 2 divided by 1. That's just factors of 2. I don't have very many options. The possible rational zeros are this. Let's make a list. There are not very many. We always want to start with the easiest ones and move to tougher ones from there. Well, what are my factors of 2? 1 and 2. So I've just got +1, -1, +2, -2. That's it. Those are the only possible rational zeros. So this is going to be pretty easy to figure out what's going on, right? Okay, while we're at it, let's calculate what our possible real zeros could look like. It's a 4th degree polynomial. So what are the numbers of imaginary zeros that I could have? Could have 0 imaginary and 4 real, right? Or I could have 2 imaginary and 2 real, good. Or 4 imaginary and no real, and then we can't do this problem if that's the case, because we have to be able to find at least 1 real zero so we can whittle this down a little bit. We don't have any technique. Until we get to calculus, we don't have a technique then for doing this. Yep. There are none. You're right. So what's that tell you about the number of positive real zeros? 0. There's no sign change, so there are no guaranteed. There are absolutely 0 positive real zeros. So what's that tell us about our list up here? Well, no, it doesn't mean there's 4 imaginary. We could still have 4 real, but they might all be, we haven't looked at the f of negative x yet, right? Okay, but the fact that we know we have 0 positive real zeros, what's that do to our list of possible rational zeros? Yeah, look, I can cancel those guys off. Or sorry, I get the wrong ones. Yeah, I can cancel those guys off, right? See my point? Now, so if we're calling this f of x, so I guess we did that, right? We said f of x was x to the fourth plus 3x cubed plus 3x squared plus 3x plus 2, then what's f of negative x going to be? Okay, but you don't even have to really think about it because it's an even power of x. So does the sign change? Stays the same, right? Does that make sense? So this one stays the same. That one's changing, right? That's going to change from negative or from positive to negative. Even stays the same. Odd power of x swaps. Even stays the same. So now we do get some sign changes, don't we? If we track those sign changes, look what we get. Yeah, we get 1, 2, 3, 4. So we have, what are the possible number of negative real zeros? I could have 4, or I could have 2, or I could have 0. I know I've got 0 positives. Gosh darn it. There. So what are the additional number of potential imaginary zeros? Yeah, we're just going to go 0, 2, and 4. So that's it. Those are the only possible ways that this thing could break down, right? Okay. So what do? Well, now we got to try it out. So here's what we're going to do. We're going to run this thing through synthetically, right? We need to get 0 in the remainder box. So we're going to set up tabular synthetic division here, which means I'm going to make a vertical line and I'm going to make another vertical line. So this is the vertical line that corresponds to the front of the bracket. So all we're going to do is write in the top row. Well, the top row would be, if we're looking at f of x, what would my coefficients be, Colson, that I would write in the top of my synthetic bracket? Well, no, we're looking at just f of x. 1, 3, 3, 3, 2. Is that what you said? Okay. And then what we do is we put another vertical line that separates the constant. And so this corresponds to the remainder box then. Okay. We're going to put a number out front that we can addition. So we'll try -1. How about? I'm going to put a -1 there. And we're going to run this through synthetically. So that's the number out front. This is the top row of the bracket. And we have to do a little bit of mental math because we're going to skip the middle row and the lower row inside the bracket. We just do in our head. We don't write that one down. What we write down is what goes below the bracket. Okay. So what would go below the bracket first? 1. Then what would I do? Okay, I multiply by -1 and I add to 3. I got to do that in my head. So what's that give me? I get -1 plus 3 is 2. So that's the next below number. What would the next below number be? Well, I get -2 plus 3 is 1. 1 times -1 is -1 plus 3 is 2, right? Good. -1 times 2 is -2 plus 2 is 0. Bingo, we got it, right? Now, what if that one didn't work? If that one didn't work, I would just cross that row off, cross that number off, and go down and try another one. See my point? Okay, but it did work, right? It did work. So what's that tell us then? So it tells us that -1 is a 0. So what's the factor that goes with that? X plus 1, right? You see my point? Okay. Okay, so then what can we do with this? Okay, well then we know that my polynomial f of x, right? This thing that I'm setting equal to 0 is going to factor into what? Well, it's going to factor into x plus 1 times all this stuff. Isn't that's my constant, right? That's the remainder is 0. So constant, coefficient of x squared, coefficient of x cubed, right? So I get x cubed plus 2x squared plus x plus 2 all that stuff equals 0. Okay, now if I couldn't factor that orange one, I would just keep going, right, with synthetic division. But I can't. That one I can factor by grouping, can I? It's 4 terms. And look, the coefficients 1 over 2 equals 1 over 2, right? So I can factor that by grouping. So I would just do that. So now I got this thing solved. I've got x plus 1. If I factor the GCF out of the first group, what is it? X squared, right? So I could take inside the orange brackets, I can undistribute an x squared, leaving behind what? X plus 2, yeah. Okay, so then I've got my plus sign between the groups. I already know it's going to work. So what factor is guaranteed to be in group 2? Well, the binomial one has to be in both, right? So I know I've got an x plus 2 times 1, right? Okay, so then what? Well, now I'm going to pull that x plus 2. I'll factor it out front with the green factor, and I got this thing. X plus 1 times x plus 2 times what's left over? There you go. X squared plus 1 equals 0. So now we're done. We've got it broken down to where I have quadratic or smaller factors, so I applied the zero product property. What are my zeros? Well, I already knew that one. I already found it up here, right? -1 I knew was a 0. I can add -2. So look, that was on my list, wasn't it? -2 was the other one I could have tried, right? And then this one right here, I would have to set equal to 0 and solve. If x squared plus 1 equals 0, what would my two solutions be? Plus or minus I, right? Because I'm going to subtract the 1. I'm going to get x squared equals -1. So x equals plus or minus the square root of -1. So plus or minus I. So what was it then? It looks like this was the winner. That was the row that actually panned out. Yep. The possible rational zeros. Okay, I got those because these are all the fractions I could make from factors of 2 divided by factors of 1. Factors of the constant divided by factors of the leading coefficient. Okay? Make sense? Okay. So this is particularly useful when we have problems like if I have a leading coefficient of 1, rational root theorem gets pretty simple because I can run integers through synthetic division really quickly to cancel them off if they don't work. Right? Fractions take a little bit longer. So this example I gave you earlier, this really ugly one, I mean, that's pretty bad, right? That would have been a reasonably tough problem to do because you gotta find a bunch of weird fractions, and they all were fractions. All the zeros were fractions, so it's not like I could have. You'd always want to try the integers first. I would have gone through all the integers first, and none of them would have worked. That would have been a pretty depressing problem to do, right? But you're not going to get any that bad. Let's try another one. Okay, give me 1 to 5 right now. Is this starting to all come together a little bit? There's quite a few moving parts in this, right? Okay, but isn't this now? Honestly, you got to kind of embrace your inner nerd a little bit here, right? I mean, you're getting to do something that's a little bit more meaningful here, right? I mean, these aren't just hokey made up problems like you've always done in the past. These are actual, you got to think about this, and you have to follow a strategy. I mean, problem solving is, people pay big bucks for people that can problem solve. So if you learn to do this stuff better in college, and if you want to make money, you will make lots of money because people pay lots of money for people that can do this stuff. And how come? Well, because it's not easy. I mean, it takes practice. If it was easy, everybody could do it, and we wouldn't have to spend all this time learning it. But it does take a lot of practice. And the people that are the best problem solvers are mathematicians and physicists because that's all they do is solve problems. So if you do one of those types of fields, engineering, physics, math, I mean, even if you don't end up going into those fields, like I say, I mean, people will pay you to go into quantitative economics. They will pay you just ludicrous amounts of money to go solve problems so they can make more money in their banking transactions on Wall Street. And if they can increase their yield by 0.1%, that adds up to, tens of billions of dollars over the course of a year. And so what if you only get to keep 5% of that? That's pretty good. How many tens of millions of bucks did you just make? Right? So it can pay off, right? Financially, if you want it to. Okay, so what about one like this? Now they give us some additional information on this one, right? This time they gave us a little snapshot of a graph. Okay, so what's this mean? Here's the function that's being graphed. It wants us to find all the zeros. They give us an incomplete graph of the polynomial where you can see that the polynomial is cutting through the x-axis. How do I know that? It's all contained right there in that information. It's pretty small, but what this tells us, it says this is 0. Here, let me make that bigger. So it says this. You need to be familiar with this because this is graphing calculator lingo, and you're going to use graphing calculators a ton when you get to college. So this little box down here says it is 0, 2.5, 0.25 by -10, 10, 1. What do you think that means? It's telling me what the graph is showing. I'll give you a hint. No? Two-dimensional. This part right here is the function, right? This is the part that's being graphed. The rest of it is just the window of the graphing calculator that you're looking at. But this is telling you what the window shows. What do you think that information's telling you? What? It's telling you, what is it again? No, it's nothing that useful. All it's telling you is the size of the window. It's telling that the x's are going from 0 up to 2.5 in increments of 0.25. So the dash marks are every 0.25. So then what's that x value right there? 2.5, that would be 2.25, right? So that would just be 2. Agreed? What do you think this is telling you then? Yeah, the y's are going from -10 on the y-axis up to +10 in increments of 1. Every hash mark is 1. Okay, make sense? So all we care about is that this is the x-axis and the 0 is at 2. So what it's telling us, 2 is a 0. That's what the graph tells us. Okay, that's pretty useful, right? That's pretty useful. If 2 is a 0, I'll write it up here. How can we use that to our advantage? Okay, right. So that means that x minus 2 is a factor. So that's another thing we know, right? Yeah, so that tells me that if I run 2 through synthetically, I know I'm going to get 0 as an outcome, right? So that tells me that this is going to, if this whole thing is equal to, well, that whole thing's equal to 0, it's going to factor into x minus 2 times another factor that's what degree? That'd be cubic, wouldn't it? Right? Some cubic polynomial that we have to figure out. We'll call it c for cubic of x. Okay, but I can find c of x. C of x is what I get when I just divide my function by x minus 2, right? We can do that synthetically. Okay, so let's do that. My coefficients would just be what? 4, negative 16, negative 8, 16. Oh, and look what else could I do something else to this function? Yeah, why not, right? Divide by 4. Right? If I'm just trying to find the zeros of this thing, I'm just setting this equal to 0. Why wouldn't I just divide this whole thing by 4? Right? And that turns this into x to the 4th minus 4x cubed minus 2x squared plus 4x plus 16 equals x minus 2 times some cubic, right? That makes it quite a bit easier, though. I get smaller coefficients now. That's going to make my list of possible rational zeros a lot smaller, too, isn't it? Right, when I eventually do that. Okay, so let's divide this out. So coefficients are 1, negative 4, negative 2, 4, and 16 with a remainder of 0. And my leading coefficient, or sorry, my 0 would just be 2. Agreed? Okay, I run that through, and what do I get? So I got 1, negative 2, negative 4, negative 6, negative 12, negative 8, negative 16, 0. Okay, so it tells me what c of x is, right? C of x is just that. I just need to find the zeros of that polynomial. All the rest of them are contained in that smaller polynomial. This ends up being a smaller problem, right? So now all we've got to do is just, let's see, that's going to be my x squared, x cubed. So I get x cubed minus 2x squared minus 6x minus 8 equals 0. I need to find those zeros, right? Okay, that one I cannot solve by grouping, can I? So I'm going to have to find another 0 somehow. But here's where I can use the rational root theorem. Let's make a list of possible zeros. Colson, how am I going to find those? How am I going to make the list of my rational zeros? Factors of what divided by factors of what? Yeah, well, positive and negative factors of 8 divided by factors of 1. So I'm going to include always the positives and the negatives, right? Okay, that's good that I've got a 1 in the denominator. These are all just integers, right? So what are the factors of 8, starting with the smallest? Well, I've got 1 and negative 1. Keep going. 2 and negative 2. 4 and negative 4. 8 and negative 8. So that's not bad, right? I've got a reasonably small list there. Plus, we can use Descartes' rule of signs. Okay, so if I look at I don't have to look at the original function anymore, right? All I need to do now is look at this cubic function. That's the one I'm trying to solve. So what does Descartes' rule of signs tell me? Let's count positive sign changes of f of x. So that's going to give me, let's see, I'm going to have, if I do that, I'm going to get a sign change, just one, right? Everybody see that? So what are the possible numbers of positive real zeros? 1. That's it. 1 is guaranteed. I know I have one positive real zero. How many negative real zeros? Well, real quick, we could calculate f of negative x. Odd powers change signs of coefficients. So the first one's going to change, isn't it? We're going to get a negative x cubed. X squared stays the same. Agreed? Next one, same or different? Different. So that becomes a plus 6x, and that stays a minus 8. So now I end up with, let's see, I've got there's one, and there's one. So my number of possible negative real zeros? 2 or 0. Yeah. So I get either 1 and 2 and 0, or 1 and 0 and 2. There's only 2 possible outcomes, right? Okay, so then now we can just start trying roots. And we'll make so we're going to do this with our tabular synthetic division. What are my coefficients going to be? Okay, so right up here, isn't it right? So I'm doing f of x. So I've got 1, -2, -6, -8. Where's my next vertical line go? Okay, right there. Good. So this is my remainder column, right? And now we'll just try values out front. Let's try 1. So I bring you guys tell me what to write here. I bring the 1 down. What goes here? -1, right? 1 times 1 plus -2 is -1. What goes there? This isn't going to work, is it? Everybody see I'm not going to get 0? So that one we can cancel. We can take the 1 off the list. Okay, let's try -1. Bring the 1 down. -3. It's not going to work, is it? Not going to work. I'm going to get 3 and -6 is -3. Not going to work. Okay, so this guy we cross off, move on to 2. Okay, so let's see here. Let me scoot this thing up a little bit. Once we get 1 hit, though, we're done, right? Because if I get 1 0 that works, this cubic is going to turn into a quadratic, which is no big deal. We can solve. Okay, so 2. Let's see. I bring the 1 down. 1 times 2 is 2. Okay, this is looking better. 2 plus -2 is 0, right? Not quite going to work, though, is it? 0 times 2 is 0 plus -6 is -6. Not going to work. We're having a rough time. So 2's off the list. Let's try -2. Okay, bring the 1 down. 1 times -2 is -2 plus -2 is -4. Times -2 is 8. Plus -6 is -2. Still not working. Okay. But at least our list is getting a little bit shorter. Okay, what about 4? Bring the 1 down. 1 times 4 is 4, plus -2 is 2. That's going to work, isn't it? 2 times 4 is 8, plus -6 is 2. 2 times 4 is 8, plus -8 is 0. Right? So there's our winner. Okay, so we know that 4 is a 0. And now all we have to do after that is find the zeros of this quadratic factor. Right? So we're just going to set x squared plus 2x plus 2 equal to 0 and solve. Okay, well, that's no big deal. How would we solve that quadratic? Probably quadratic formula, because we don't have magic numbers, do we? Right? So then x equals what? So -2 plus or minus square root. Okay, 4 minus 8. 4 times 1 times 2. Good. So 4 minus 8 divided by 2. Okay, so that's giving me, if I split the fractions up, -2/2 plus or minus square root of -4. What's that? 2i over 2. So then we just get our solutions would be x equals -1 plus or minus I. So we got them all, right? And which one was it? It was this guy right here, wasn't it? We found 1 positive 0 at 4 and 2 imaginary out of our cubic that we were solving. Okay? Okay, how are we doing? Is that moving up the ladder? You getting this? Okay, let's look at one more, and then I think we're good. So what about this one? Okay, this is one where, what do I have? Oh, that's it. Yeah, this last one. Okay, so they don't give us any hints, right? So we've got to just make a list and try this sucker out, right? So well, I guess let's do Descartes' rule of signs first of all. So for f of x, how many sign changes? One. That's it. Everybody agree? Positive to negative, and then it stays negative. So what's that tell me? One positive real zero, exactly. How about negative? So if I do f of negative x, what's my first term going to be, Mason? X to the fourth. What's the next one going to be, Jimmy? Yep, that's going to change to a plus 4x cubed. Next one, Griffin, what's the next one? Okay, that one stays negative. Next one, Colson? Good, plus 44x. Last one, what's that going to be, Shane? Positive or negative? Negative, right? It wouldn't change, right? Because it's an even power of x. Negative 15, there's nothing to change it. It just stays the same. So now what do we end up with for our sign changes? Let's track our sign changes on that guy. So if we look at sign changes, I got positive. There's a sign change. There's a sign change. There's a sign change. Everybody agree I got 3? So what are my numbers of possible negative zeros? Negative real zeros? 3 or? No, 3 or 1. Goes down in increments of 2, right? So 3 or 1. So then we end up with either 1, 3, 0 or 1, 1, 2, right? No, we can't get 2 because this one, if we get 3 sign changes, then it's either 3 or we drop down in increments of 2. Okay, so that's it. Those are the only possible outcomes. Okay, let's make a list of our possible zeros. So I want factors of what divided by factors of what? Positive and negative factors of what divided by factors of what? What's that going to be, Oscar? The rational zeros, the numerators are going to be built from factors of 15, the constant. So factors of 15 divided by factors of 1. Okay, factors of 1 are just 1. Okay, so that's pretty good then, right? What are our possible outcomes? 1 and negative 1, 3 and negative 3, 5 and negative 5, 15, and negative 15, right? So there's not that many. And if we get one positive real root that works, well, that's all we need is 1. Actually, no, we need 2, don't we? Because this is quartic. But if I get one positive one that works, I could cross all the other ones out because I know I only have 1, right? Make sense? Okay.